Okay. So by now, everybody should see my screen if you're logged in on a computer. Okay. This is the electrical symbol sheet that is actually assigned as one of the assignments to try to figure out what symbol is which. Okay, we've talked about some very easy ones. So, for example, can anybody tell me what 15 is here? What symbol 15?
Double pull, double throw.
Double pull, double throw, switch. What about 12?
Single pull, single throw.
Single pull, single throw. That is correct. Now, what about number 4? It was in your reading. It's been in your reading material. It's been on the symbol sheet that I put out there for study purposes.
Hey, Lockie, we all know you know these, buddy. Come on. Let these new guys get a chance.
It's okay to be wrong and guess. No one's going to beat you up over being wrong yet.
Is a fuse?
Okay, one of you existing guys, tell me what it is.
Looks like a fusible.
Yeah, it's a fuse. Okay, what about number 17?
Single pull,
double throw.
Single pull, double throw is correct. What about number 18? We haven't really talked about this one yet. What's number 18?
I was going off of your slide, but I couldn't completely read it. It's an inline thermostat overload, I think.
How about just a push-button switch? It's a push-button switch. It's a normally closed push-button, so when you push down on the plunger, it opens. What about number 11? We're going to be talking a lot about number 11 this term. Anyone want to take a guess?
Thermostat that closes on rise.
You have to say that again. I didn't quite hear that because there's some background noise.
Thermostat that closes on rise.
Yeah, it's a cooling thermostat. It's going to close as the temperature goes up. The cooling thermostat. That's going to be the thermostat we use for most of this term. What's number 3?
Red light, red signal light.
Just a red indicator light. Just a light bulb. What about number 7?
It's a regular thermostat.
It's a heating thermostat. Closes on temperature drop. Because you see how the little switch is in the up position. It's going to close as the temperature drops. What about number 19?
Isn't that one?
Just a red indicator light, it looks like.
Yeah, it's just another indicator light. Okay. Oh, what about number 16? We talked about it a little bit, but we're going to spend a lot more time going into it.
Transformer.
Yep, transformer.
What was number 20?
Hey guys, I have a major favor to ask. Whoever's eating and chewing at the same time, would you please mute yourself? Thank you. And I can see who it is. I just don't want to embarrass anybody. Okay. What about number 6?
Coil.
Number 6. What was that? You said coil?
Is it a crankcase heater?
Yeah, it's a heater. It's a crankcase heater. It's different from a coil on a schematic diagram because it has the little squares, sort of like the top of a castle wall. If it's a coil, it's going to be a loop of wire. Okay? Coils you're going to see drawn in a couple different ways. You can sometimes see them drawn as a loop of wire, just like you would have in a transformer, or you can actually see them drawn more like this. People draw coils at. Okay, that's a coil. Okay, and so I think that's where. So if you take a look, by the way, this lab assignment is something I did assign, so I've basically done half your lab assignment for you.
Hey, Chris, what was number 2?
What was that?
What was number 2?
I didn't touch on number 2 yet. It's a 3-phase compressor.
Okay.
Because you have 3 windings, equal length. We haven't even talked about that yet, so I don't want to totally confuse everything yet.
Okay,
that's why I sort of made this.
Because I didn't know what the difference between number 2 and 10 were.
2 and 10. This is you see that number 2 has 3 windings that come together. So you have an L1, L2, L3.
Yep.
Number 10 only has 2 windings, a start and a run, coming into common. And again, I don't want to confuse the first termers that are on here at all. So that's why I didn't touch on those yet. Okay, we need to talk about some motors still. Okay, so that's our symbols for the day. Okay, so that's on the symbol sheet that's in your course. In the course material from, I think it was yesterday, there's a basic symbols lab there. And somebody did message me they couldn't get into lab number 2. That's fixed now. There's a basic symbols lab there. Don't try to do this all at one time. It's not due until next Monday and Tuesday. Don't rush to get it done because there's stuff ongoing over in the meantime that's going to affect those labs. Okay, so all of this stuff is due next, the homework is due next Monday, and the labs are due next Tuesday. Don't rush to try to turn this stuff in today. Okay, get it in by the due date. One other housekeeping thing that I do need to talk about before we start on today's material. You have daily announcements out here that give you directions on different things that I'm asking you to work on. Okay, so if there's ever an alteration to a worksheet that I need to change something, okay, all of the directions are always going to be in my daily announcements. The daily announcements always post around 4 o'clock in the afternoon the day before. Like today's stuff posted 4 o'clock yesterday. That's just habit. I do it, everything posts by 4 o'clock in the afternoon. So please make sure that you do, that you look at this stuff. And someone asked me in the discussion board, are the new students supposed to do the assignments? The answer is yes. We're going to talk about that when you hang out after the call. Okay. The other thing I need to talk about is discussion boards. You guys are all being great about getting into the discussion boards and posting your here. Please answer the questions that I'm asking you in the discussion boards, specifically the ones related to electric. Going in and saying you're here but not answering the questions tells me from an attendance standpoint you're here, but from a grade standpoint you didn't answer my question. Okay, so please go in and answer my questions when you post in the discussion boards. It's very important. Okay, again, just saying you're here, yeah, that takes care of my attendance, but it doesn't take care of the fact that the discussion boards are graded. Okay, so answer my questions. Okay. Having said that, let's go ahead and talk about a little bit more about series and parallel circuits. Again, some of this is repetitive. It's designed to be. Okay, and I'm going to play 20 questions as we go through this also. So, talking about electrical circuits, because this is the core of air conditioning, okay? And again, some of this is going to be repetitive. That's okay. With a direct current circuit, current travels in one direction, and you saw that when we've been messing around with the simulator. Okay, current travels in one direction. Negatively charged electrons flow to atoms with a positive charge. So in a direct current circuit, current flows from negative to positive. These are electrical circuits most often powered by batteries, and they're the electrical circuits that are in our high-tech electronics, okay, like our computers and stuff like that. That's stuff we have direct current in, okay? So direct current is known as DC. Alternating current. Okay, alternating current is most commonly used power source in HVAC. Okay, it's what's available in our houses. Okay, it's what we have our 60 hertz frequency, and the electric symbol for alternating current power supplies down here at the bottom. The electron flow continually changes direction. Okay, it changes at 60 times per second. Okay, which gives us our frequency of 60 hertz. Okay, alternating current is more economical to produce than direct current. Okay, that's why we use it. It's more economical to produce. Direct current has a lot of line loss over long distances. You'd have to have a power plant about every 5 miles to properly use direct current in households. Okay, it's also at higher voltages. It's a little bit more dangerous than the alternating current is, again, because that reversing of the flow of the current. Okay, parts of an electrical circuit, we have 4 parts. We've been talking about this. I have to have a source. Okay, it provides the source voltage for the circuit. I have to have a load. Okay, the device that uses electrical power. Okay, it does something to create work. Okay, it could be a motor, okay, which is called an inductive load because it has a coil, and it could be a resistive load such as a light bulb. Now you have to start being careful with light bulbs, okay, because we have a lot of LED light bulbs out there. They're no longer resistive loads. They're now inductive loads. So we have to be very careful when we start looking at light bulbs these days because you don't know if it's the old style light bulb or not sometimes. You have to have a switch. Okay, it controls the operation of the load to turn it on or off. Okay, a load without a switch will run forever. Usually not a good thing. It has to have conductors. Okay, the conductors provide a path for the current to flow. That's your wiring, or on a circuit board that could be your the gold plating or the silver part of the circuit board. What's another conductor that someone could tell me about? Someone give me an example of another conductor other than wiring.
Metal.
Anything that's metal. What else?
Us, our skins.
Water.
Yeah. Humans are a great conductor of electricity. Be careful.
Yeah, there's water.
Okay.
Humans?
What was that?
Water.
Water, yup. Okay. What's an insulator? Give me an idea of an insulator. What is an insulator?
Rubber.
Dry wood? Gloves. Ceramic.
Rubber, dry wood, some type of gloves. Be careful about that. Some gloves do not do great about insulation.
Ceramic.
Yeah, ceramic. Okay, that just about covers insulators. Is concrete an insulator?
Yeah, right.
It can be.
Only if it is perfectly dry. Concrete has a habit of having enough water in it to actually provide a path for electricity to flow, even if you think it's dry. Okay, that's why we have to have GFI outlets wherever we have concrete floors, because they do hold water, they absorb water, so be very careful about concrete. If it's perfectly dry, yes, concrete is an insulator. But the minute you have any water on it, concrete no longer becomes an insulator. It's a path. Okay, so that's why you have GFI outlets in your garages and any place like where you have tile floors on top of concrete. Okay, so here we come back to our open and closed switches. Okay, we have our top circuit here.
What happened?
Okay, our top circuit here, we have what's called an open switch. Okay, the light bulb is not on, the switch is off. Okay, tell me a little bit about if I am taking a voltage reading from here to here.
OL?
Okay, volts, what am I going to get?
OL, right?
You're going to get 15. You're going to get the source.
Voltage.
You're going to get the source.
Yes, I'm going to get source. Okay, so volts, I'm going to get 115 volts. Because what is the rule of electrical I'm talking about here?
Difference?
Well, it is a difference. I have neutral, which is effectively 0, coming back to here. Okay, and I have my hot, which is effectively 115 coming to here. But I gave you a rule that always applies. Voltage across an open switch is what?
OL?
No.
Source.
That's resistance.
Voltage.
Source.
And close is 0, right?
Voltage across a closed switch is always 0. So if I take a voltmeter lead here and here, it's going to be 0. Okay? So volts. Right. Source across an open switch, 0 across a closed switch. Now let's say I disconnected the circuit from electrical. Okay, in other words, I no longer have power on the circuit because we cannot take a resistance reading with power on the circuit. If I take my resistance reading, and someone kept saying this earlier, so now say it. What is my resistance across an open switch?
OL.
OL. Or, what does OL stand for?
Open line?
Infinite.
Oh, infinite line?
And open line is correct, okay? I just want to get the word infinite here at as many times as I can, because for those of you who have to take licensing tests eventually, it's not going to say OL, it's not going to say open line, it's going to say infinite. Okay, resistance across a closed switch.
Damn, I'm slow.
Have another cup of coffee. Resistance across closed switch.
Is the power on or off?
Off. Anytime we put an ohm meter on here, we have to shut the power off.
Oh yeah, it should be
0.
So resistance across a closed switch is always 0. Okay. Turn the power back on here, okay? I can't erase my little lines there easily. My voltage from here to here with the circuit drawn as is what?
Some number?
Should have none.
Voltage.
Should have no voltage.
It should be 0 because I have an open switch in the circuit. I'm not going to have any voltage. Again, there's nothing getting down here. There's no hot coming down to the bulb.
Yeah.
Voltage right here across this single bulb.
115.
Someone said it softly. Say it again.
Should be 115.
115.
Yeah, it should be source. 115 in this case. Okay, because voltage across an energized load is source.
The source?
Yeah. Okay, now I'm going to turn the power off again. We're just turning the power off. I'm putting my ohm meter on here. Resistance across a load is what? Well, it could be 0, but that would be a problem, wouldn't it? It's some number. Resistance across a load is some number. What is the problem if I have a 0 resistance across a load?
See, there's either a problem in the load or the line before it.
If I have 0 in a load from here to here, I have a bad load. It's a shorted load.
Oh.
What if I have an OL from here to here? What if my meter reads OL? What can you tell me about the load?
Could be 2 problems. It could be either something wrong with the load or a wire before it.
Yeah, it's either going to be in the connection or something's wrong with the load. So you pull the bulb out and just ohm the bulb out. Okay. So a switch, as we know, passes power when it's closed. Okay, and again, please mute yourself if you're not answering a question. A switch passes power when it's closed. Okay, the fuse passes power until a power surge burns it out. A thermostat is set to pass power to the light bulb when the temperature drops below 35 degrees. This is a heating thermostat. So all of these things are considered what in a circuit? There's a word for all of these devices. What are they considered? Well, they're
Are they safety switches?
If we look at how they're wired, they're in series, right?
Yeah.
But what are they? What do we consider these devices in a circuit?
A direct
series switches?
Control devices, right?
Yeah.
So these devices here, and my writing is lousy with the mouse, so sorry about that. Okay, they're control devices.
Oh.
Okay, what's this device here? What is this device right there?
Is that a fuse?
It's a fuse, but if I put in classifications of controls, is it a operating control or is it a safety control?
Safety?
It's a safety control. Okay, because a fuse is designed to burn out if we have an unsafe condition. For example, we have a number of these burn out every term in shop because people wire stuff incorrectly the first couple times. We keep bunches of them on hand for this. Okay? A fuse is designed to burn out when there's an unsafe condition. Okay, but these other controls here, the switch, the thermostat, they're operating controls. So you have two types of controls. You have a control devices that are all the controls put together. You have operating controls that turn whatever you're using on and off, and you have safety controls, okay, that deal with unsafe conditions. Now, having said that, if we go back to our if we go back to our diagram and take a look at the devices that I circled on your symbol sheet, number 11, is it an operating control or a safety control?
50. 11 is a operating control?
Yeah, it's a thermostat. It's going to turn something on or off based on temperature. It's an operating control in this case. Could it also be a safety control?
Yes.
Isn't there a high limit in safety control or something?
Past the desired.
Yeah, but a high limit, for those, again, I don't want to confuse people who haven't had the gas and oil term yet. Number 7 would be your high limit, right?
Yeah.
Because we want it to open if the temperature goes too high. Okay, number 11 closes on a temperature rise. So would you ever see that as a safety control, or is this always an operating control?
You can see it as a safety control too. You said it opens on temperature rise?
This number 11 closes on temperature rise.
If it closes on temperature rise, then I think it's a safety.
No, this is your cooling thermostat that's on your wall. But could it be used as a safety?
Yeah. Yeah. It can be.
Everybody who had refrigeration in a prior term has seen this before as a safety device.
Yep. Okay.
Okay. What about number 4? Is it an operating control or is it a safety device?
That's a safety, right? Device. That's a fuse.
Yeah, it's a fuse. It's a safety device. Okay, now I'm going to toss 2 more in here. Actually, if I can get a circle in here, will be awesome. Okay, toss 2 more in here. What type of control is number 13?
Operating.
Well, what is it at first? We haven't defined it yet. What is it?
Pressure switch. Thermostat.
Okay, it's a pressure switch. Anytime you see the little device with the plunger on the bottom, it's a pressure switch. Okay, thermostat looks slightly different. See the difference on the 2? Okay, the little plunger. What was that?
I said, which one is the thermostat?
Thermostat is number 11.
All right.
So he was just talking about 13.
So now I'm talking about 13. Okay, the little plunger on the bottom is anytime you see the little plunger, it's a pressure control. Now, what type of pressure control is this?
Temperature drop?
Pressure.
Oh, pressure.
So it opens on pressure rise. It opens on pressure rise. You see how as it goes up, it opens. And it closes on pressure drop. So this is considered a high pressure switch. Okay, high pressure switch. Okay, opens on pressure rise, closes on pressure drop. What about number 5?
Pressure? Low pressure switch. 13.
You're right, low pressure switch. Because it's going to open on a pressure drop. Okay, again, look at the direction of where things open. It's going to open on a pressure drop, and it's going to close on a pressure rise. Okay, so we've introduced the high pressure switch and the low pressure switch. Now let me ask you, in air conditioning, do you think that these are safety devices or operating controls?
Operating. There could be both.
Both are operating control.
Okay, I hear one person, I hear a couple people saying operating controls. I hear a couple people saying safety controls. Okay, you're actually both right. Okay, number 13 up here, which is my high pressure control, is usually a safety. My low pressure switch is both a safety and an operating control. Okay? Low pressure switch is both a safety and an operating control. And again, we're going to spend more time on this. Right now, it's all about symbol identification. Okay? So we've added those two additional. Any questions on these two? Okay, back to my PowerPoint that I've scribbled all over. Okay. We have 3 electrical units of measurement that we're really concerned about. Okay, we need to worry about voltage. Voltage is also known as electromotive force. Okay, we have to worry about current. Current is known as amperage, okay, also known as amperage on your meters. It measures the amount of electron flow per unit of time. It's measured in amperage. And just understand, for some reason, there's also letters designated to all of these. We'll get into the some reason in a minute, that you're looking forward to that. Okay, resistance is an opposition to electron flow. It's measured in ohms, okay, which uses the little Greek ohm symbol, but it's also indicated by R. I most often use R, or I type out the word ohms when you're looking at stuff, because for the life of me, I can't draw that symbol. So I'm fine if you draw the symbol. I'm fine if you put the word ohms. I'm fine if you put R equals and a number, okay? Just tell me when you write something down on resistance what the unit of measurement is. It's either resistance, which is ohms, or it's current, which is amps, or it's voltage, which is V. So just make sure you designate what we're talking about. Okay, but we have 3 units of measurement we have to be worried about. We have voltage, current, and resistance. They are in every circuit that's energized. Okay, the only one that occurs in non-energized circuits is resistance. Okay, because we can't take resistance readings in energized circuit. It's there, but we can't take the reading in an energized circuit. We have to calculate that. Okay, because you cannot use an ohm meter on an energized circuit. And I can promise you there's a question of that on your final exam. Okay, that's going to try to get you to say you can put an ohm meter on an energized circuit. No, you cannot take a resistance reading on an energized circuit. Your meter will melt down. It will blow the circuit boards inside if the voltage is high enough. Don't do it. Okay, so all of this comes together in some guy way back in the dark ages dreamed up Ohm's law. Okay, Ohm's law mathematically proves the relationship between voltage, current, and resistance. Ohm's law states that it takes 1 volt of electrical pressure to push 1 amp of current through 1 ohm of resistance. Okay, that's Ohm's law. 1 volt of electrical pressure to push 1 amp of current through 1 ohm of resistance. Now, they've tossed letters in here, and I always think that anytime someone mixes letters and numbers together, something bad is going to happen. Okay, but the bottom line is that E equals I times R. We look at this. 1 volt, 1 amp, and 1 ohm. That's the mathematical relationship with Ohm's law. So when we want to find what the resistance is of an operating circuit, we have to use Ohm's law. And you'll think we never need to do that. But yeah, unfortunately you do. Okay, we use it quite a bit, and it becomes second nature, but and also this is going to be on every single certification or licensing exam you're ever going to take. And I took a licensing exam probably 6 years ago now in Florida, and there were grown people crying over Ohm's law. So just, again, always remember Ohm's law, okay? E equals I times R. Once you have those letters, you can do anything with them. So current, you take that same formula, you redo it, okay? If you're looking for current, which is I, you take your voltage divided by resistance. Voltage is current times resistance. Resistance is voltage divided by current. Then we toss in power, which is W. It's voltage times amperage. Power is watts. It's how much power, how much work we're doing with the current. Okay, these are the 4 basic formulas of Ohm's law. Okay, now you can actually pull this back to what we consider the pie chart, and I'll show it to you in a minute. Okay, if you think about it in a pie, okay, you can actually draw a circle, take your slices of a pie, and E, which is voltage, equals I times R. So if you're ever asked an Ohm's law question on an exam and you have scrap paper, just immediately write down the pi formula here. Okay? We can do the same thing with watts. Okay, we can do P equals E, which is voltage, times I. Okay? And again, there's printed...
like V for voltage.
P. Oh, E is voltage. E is always voltage. And how they came up with that is going back a screen. It's electromotive force. Okay, is the formal name for voltage. So they use E from EMF.
Oh.
Okay, yeah, we have to change the letters around just to make it more difficult for you. Questions? Guys, this is one of these things. Memorize it. You're going to use it forever. Memorize it now. It will make it easier for you in the long run.
Take a screenshot.
Okay. What was that?
Just write it down.
Yeah, and you also have in your module for today is all my slides. Okay, they're available as the student handouts there. They don't have my scribbles on them, but all my slides are in the handouts. Okay, so you can always find it there. Okay, now here's the thing, and I'm sure some of you who've already had prior terms have noticed something when you're in the shops, and I'm not sure if it was ever explained to you. Okay, when you do some of these labs on alternating current, the numbers don't work out. Okay, so again, we have our basic series circuit. Okay, we've drawn our line, we have our switch, we have our light bulb, and I'll do this neater in another diagram when I get off the PowerPoint. Okay, we have our switch here. Let's say my light bulb, I measure it out disconnected from the circuit. I have 1 ohm of resistance. Okay, that's a 1 ohm. Okay, I have 120 volts. What's my amperage? Okay, so strictly speaking, if we go back to the last slide, amperage is current. Okay, so current is voltage. Yeah, voltage divided by resistance. Yeah. 120 divided by 1. Okay, now, if I have a current of 120 amps, think about that. If I have a current of 120 amps, what is going to happen to my circuit breaker? It's going to blow the circuit breaker, right?
Mm-hmm.
Because most houses only have 200 amp service coming into it. Okay, and your circuits in the shops are only going to be 20 amps. Most air conditioning systems, my breakers are 40 amps or 50 amps at the most. Okay, so why does my amperage not work out? I can plug a light bulb in with 1 to 3 amps of resistance, and it will run perfectly fine on a 120 volt circuit. So what happens when I plug that light bulb in? A light bulb has a coil in it. The filament is actually a coil. So anytime I plug a coil of wire in, it generates its own resistance because the magnetic field around the coil has resistance. Okay, the magnetic field around the coil creates resistance. That's called induction or inductive resistance. Okay, induction, inductive resistance is that magnetic field that's generated. You can't measure that in a circuit. That's why the calculations only work in a purely resistive direct current circuit. Okay, so again, when you go and do these in the shop, when we get back on campus, your measurements are not going to totally work out. Okay, you'd be surprised how many times I get shop projects when people are on the wiring boards where miracles happen and the measurements exactly calculate out to Ohm's law when you're on an AC circuit. It tells me one thing, that you didn't believe your meters. Okay, trust your meters. Any questions? Okay. So, to find voltage, when you draw this pie chart like I was telling you about, to find voltage, put a finger over the E. The two letters next to each other means multiplication. To find current, put your finger over the I. When you have letters above each other, you divide. To find resistance, put your finger over the R, and again, letters over each other is division. Okay, so as long as you remember how to draw the chart, you can find any of the formulas just by the three slice pie, basically. And again, you can do the same thing with power. Okay? Power is wattage. Okay? Wattage is P I, and this one's easy to remember because it sort of spells pi, E. Okay, so again, if I know the power and I know either of those other two values, I can find the missing value. Sort of makes sense to everybody? Okay, there's people who spend weeks on Ohm's law. I don't want to spend weeks on Ohm's law. I want you guys to know how to use these pie charts and understand that there's a relationship between power, amperage, and voltage, as well as voltage, amperage, and resistance. Okay, there's a mathematical relationship. And as I said, you throw letters and numbers together, bad things happen, but you've got to be able to figure it out. Okay, and again, you can go nuts with trying to figure out wattage in different things, okay? But you don't need to. Okay, I've never had anybody who needs to use these formulas with the ease. Now, our electrical department, they spend a couple extra weeks on this stuff to learn how to do square roots of everything and stuff like that. You really don't need to use any of the ones I'm circling, okay, in our circuits and what we're using. Okay, you need to use the ones that I have not circled. Okay, this is the chart the electrical department gets to memorize. I like the circles better. Okay? When you're with your meters, okay, and when you get into shop, first of all, if you have never taken voltage readings before, when you get into shop, I expect you to ask the shop instructor to demonstrate this to you, or work with somebody who's been there for a few turns, because you don't just stick a meter in a socket without knowing a little bit what you're doing. Okay, voltage readings are taken across load switches and sources of power. Okay, amperage readings are taken with a meter that clamps around a conductor. We don't actually, in the HVAC trade, we don't put an amp meter in the circuit that often. Okay, we might, when we're talking the gas term, we might put a amperage reading into the circuit, but we don't. We normally clamp it around a wire. Okay, so you have your conductor, and your meter has a clamp that clamps around the wire. We only put it around one wire. You don't put it around both wires. So you have a line and a neutral, or an L1 and L2. Don't put it around both wires. Only put it around one wire. Resistance readings are taken on circuits that are de-energized. Okay, and with the component being checked, isolated, do I really care about that with a one light bulb circuit? No, it really doesn't matter. But do I care about it with multiple bulbs? Oh yeah. Okay, or multiple paths, because you can have the power going the wrong direction. Okay, so you need to isolate components when you're taking resistance reading. And again, circuit must be de-energized. Okay. We talked about this a little bit yesterday. I'm going to talk about it again briefly here. Electrical circuits that have one path are series circuit. Now, I'm adding in some portions to Ohm's law. In a series circuit, the current is the same at all points in the circuit. In a series circuit, the current is the same at all points in the circuit. The total circuit resistance is the sum of all resistances in the circuit, and I'll show this to you again when we look at some diagrams. But if I have two light bulbs in a circuit, the resistance adds. Okay, the resistance adds together. The voltage is split between all the loads in the circuit. Okay, if you have two light bulbs, the voltage gets split between the two loads, and that's dependent on the resistance of the bulbs. Now, because there's a single path to a series circuit, a break or an open device anywhere in the circuit will stop the electron flow through the entire circuit. So we have some basic rules to a series circuit. Okay, let me hop to another screen here so we can sort of make a list real fast. Okay, series circuit. Okay, amperage is the same all the way through the circuit. Voltage adds up to the total voltage. Resistance adds to total resistance. A break, or let's just say an open, any place in the circuit, stops the current. Where am I going to see series circuits most often used in the HVAC industry? Anybody? Where am I going to see series circuits most? What was that?
Safety switches.
Safety switches and yeah, safety switches and controls. So it's my control circuit. Safety and operating. Now, there's exceptions to every rule, but that's most often where you see series circuits. Okay? Amperage is the same all the way through the circuit. Voltage adds up to the total. Resistance adds to the total. And an open any place in the circuit is going to stop the current. A control circuit is where we see this most. It could be safety or operating.
Shit.
Okay, simple series circuit. And someone had way too much time on their hands when they made this slide. Simple series circuit. What type of circuit is this?
Closed.
What's the name for this circuit? Is it an open or a closed circuit?
An open.
An open.
That's an open circuit. There's a break in the circuit. What about this circuit? Open or closed?
Closed.
Yeah, it's a closed circuit. What if somebody put a wire from there to there? What type of circuit is that?
Closed.
It's still going to be closed.
Well, wait a sec. Electrical.
Parallel?
Electricity wants to take the path of least resistance, right?
Yeah.
Okay, so what do I no longer have in the path for that the electrons are going to take?
You don't have
Load.
it loaded.
I don't have a load. So there's going to be no resistance in this circuit, right?
Right.
So this becomes what we call a short circuit. A circuit without a load, or where the load is bypassed, is called a short circuit. Another term. A circuit without a load, or where the load is bypassed, is a short circuit. Now, what happens when we have a short circuit? What's the outcome?
Blown fuse.
Yeah, you're going to blow a fuse or a breaker. Okay? I ask these what's an outcome questions for a reason, because that's where we start to learn about troubleshooting. That's why I ask the outcomes. If you come up to a property which has a blown fuse or a blown breaker, okay, breaker, I normally try to reset the breaker after making sure no one's touching the equipment while I'm doing that. But fuse, you want to find out why we have a blown fuse. We don't just replace the fuse and let it blow again over and over and over again and hope that somewhere some inspirational force will come down and fix it for you. We have to find where my short circuit is. Okay? So that's why I ask about, okay, what happens if? But anytime you have a bypass of a load in a circuit where there's no resistance, no load in the circuit, it's considered a short circuit. Okay, so we have another term here. Okay, short circuit.
I have
okay,
a question.
It's one with, yeah.
So
Go on.
when you have a fuse that blows, why would putting a higher fuse, like say you have a 30 that's blown, you put a 40 in, why would that make it different?
Sometimes a fuse will blow because, for example, somebody has added an extra motor or something to the circuit, might have added extra computer equipment to an area. That's not necessarily a short circuit. That's why you do have to go find out and look. It's in HVAC, and again, I want to talk about in HVAC. Never do that.
All right.
Because HVAC equipment doesn't change that often. If you're in a house and you have to do it, it's just because people are using more than the circuit was originally designed for. Now, what can happen if you while we're on the topic, what can happen if you put in a bigger fuse?
Can't get enough energy, not enough power.
Well, the fuse doesn't control the amount of power it gets. So what happens if you have a circuit in here with let's say it's a 5-amp fuse, and it's blowing on and off, and you decide to take that, okay, we'll fix this problem. You pull the 10-amp fuse off your truck. What's going to happen to that circuit? What could happen in that circuit.
Well, depending on what wiring you have, I mean, you're going to overheat your wiring and it's going to cause a fire.
Yeah, that's my point. We don't want to increase fuses in HVAC equipment and on HVAC circuits. And again, I'm going to speak from the not wanting to be an electrician standpoint. I don't want to increase amperage and fuses on line voltage circuits either, because we don't know the size of the wire. Okay, if you go too high on amperage, for example, you suddenly have that extra air conditioner, the extra window air conditioner in a bedroom, and you go too high on the wiring, all of a sudden you take a real chance of increasing the size of the amperage in that current over what the wire can handle. I mean, you might have only 14 gauge wire going to a wall outlet. You go up over 15 amps, that wire is going to start melting down, and all of a sudden you have a fire. So increasing the size of the fuse is never really a good idea. Okay? People do it all the time. You might get away with it for years, but it's not a good idea. Okay, and again, you have an open in a circuit, it turns it off. Okay, loads in series. Okay, this slide says it is uncommon in our industry. Okay, we do not see loads in series that often. Okay, I see it most often in electric heat. I don't see it that often in cooling. Loads in series because they split voltage, but you have to know how to troubleshoot. Okay, when there's two or more loads in series, if one goes bad, what happens to the other load? If one load goes bad, what happens?
It shuts off the other one.
It shuts off the other one. Okay, so both loads are off. Anybody remember trying to find light bulbs that have gone bad on, let's say a string of Christmas tree lights?
Yeah, that takes 10 years.
Okay, it's easier to toss out the lights and get a new light chain. Okay, so that's what can happen when you have loads in series. You have to figure out, okay, which load is bad. Now, are your outlets in your house in series or parallel? You have 4 outlets in a room. Are they in series or parallel?
Parallel.
Uh-oh.
Yeah, because again, you turn one switch, you turn one device off, the others should continue to run.
Yeah.
Okay, total voltage equals the sum of the voltage drop at each load. And again, new term here. I mentioned it yesterday, but new term, voltage drop. That's the measured voltage across the load. That's how much of the total voltage the circuit is using. Amperage, as I wrote on my scrap piece of paper on the other screen, amperage is the same at all points in the circuit. Resistance follows voltage. You add up all the resistances in a circuit. Okay? And again, just an example. Okay? Heating elements. They're the only real loads that I see in series ever. The heating elements. And the reason we can put heating elements in series is a lot of times I have to put electric heat into an apartment or a condo where I don't have the amperage available for heating elements in parallel. Okay, and I can control my amperage much easier because the amperage through a series circuit is the same all the way. Now, parallel circuit is exactly the opposite. Parallel circuit, we have several rules for. There's more than one path for electrons to flow. Parallel just means next to each other. Okay, parallel circuits, the source voltage will be the same at all the loads. Okay, so if I have a source voltage of 120 volts, one phase, 60 hertz. By the way, that's what that means. 120 volts, one phase, 60 hertz. When you see a symbol like that. It's a household circuit. It's what you have in the outlets of your houses. Okay? I have a series circuit. is there more than one path for electrons to flow here?
No.
No. Okay, now what about this one?
Yes.
Yes.
Okay, this is the example, same example. I have my 3 heaters, but this is a parallel circuit. So if this generator is a 120 volt generator, okay, I'm going to have 120 volts here, I'm going to have 120 volts here, and I'm going to have 120 volts here. Okay, now, if I have in each of these, if I have 120 volts, and each of these has its own resistance, we have another law of parallel circuits. In a parallel circuit, the amperage adds. My total amperage in the parallel circuit is the amperage of this, the amperage of this, and the amperage of this. And again, I want you to think back to your houses. Okay, your total amperage that comes out of your breaker panel is every room added together. In most residences, you have 200 amp circuit. You have 200 amps in most of the newer residences. The older residences, folks, I have somebody who really needs to mute themselves. Thank you. Okay, the older residences, you may only have 100 amp service coming into it. But that's the total of all the different circuits in the house. So you take a total of everything that's running, and that comes up with your total, and it has to be under the level, under the available power. Okay? But in parallel circuits, voltage is the same at every load, but amperage adds. Okay, and resistance is a crazy math formula that we'll talk about in a minute. Okay, so again, let's put it in terms of what we're doing this term. This is a window unit. This is a window unit. Doesn't it? This would be a thermostat over here. Okay. If I take this and make it into a cooling thermostat right there, okay, closes on temperature rise, energizes a contactor coil. We haven't talked about that yet. When this gets power, it closes my 2 contacts and it energizes my compressor. The BR, which is my blower relay, closes and energizes my blower motor. Are both of these motors getting 240 volts?
Yes.
No.
Yeah.
Yes, they're parallel.
Okay, somebody said no. Please tell me where I lost you, please. Are both of these getting...
I thought that the load would have been divided.
No, when you're in a, this is parallel. So if you look here, you get 100, you get your 240 there, and you get 240 there. They both are attached to source. Okay, so in a parallel circuit, okay, we have a parallel circuit. The important things to remember, amperage adds. Okay, voltage is the same. Voltage is full source for every load. Okay, resistance I'm going to skip over for the moment. Okay, and where do we see parallel circuits used in the HVAC industry most often? Where do we see parallel circuits used?
Heating.
What type of circuit? Yeah, what type of circuit is this? We had series circuits being used as controlled and operational. What would I call this? It's the load circuit. It's the part of the circuit, part of the system that does the work, so it's the loads. Okay, most often used on loads. And again, I use the word most in there. Okay, because 99.9% of the time it is loads, but occasionally there's a reason to use it in controls. Now, if this compressor or this blower motor burns out and creates an open, will the compressor still run?
Yes. Yes.
Yeah, the correct answer is yes, because there's nothing to stop the flow of electricity here if the blower motor's burnt out. So if there's an open in another branch, the rest of the circuit keeps running. Okay? Now again, resistance we'll talk about in a few minutes. Okay, there's something weird about resistance in this series, or in a parallel circuit. Okay, but this is a basic window unit. This is a basic cooling circuit. We have two controls that are relay coils, and again, we still have to talk about relays and contactors, but when these are energized, it closes the thing with the same letter. This is why labeling is so important. Okay, so if I have the letters on a diagram, I have the C there, I have the C down there on the control device. If I have the letters, on the diagrams, which C there matches the device it's controlling there. That's why labels are so important. Because once I start looking at a diagram that has 20 or 30 or 40 different devices on it, I have to be able to see what controls what. So again, labels are important.
Now, will that C and will they have different resistance? That relay, the BR relay and the C relay, are they going to have different resistance?
Most likely, yes. What are you thinking? What are you thinking, and why are you asking that?
Well, I just was curious if they did, because otherwise, how would they control individually the different functions?
Okay, at the risk of getting too far ahead of myself, because we're going to be talking about relays and contactors. Okay. Again, when you have two loads in series or in parallel, these are next to each other, so they're parallel. They're both getting the full source voltage. Okay, but a relay has a coil and a set of contacts. This coil, which is down here, that's a coil. Okay, it's not the right symbol for a coil, but it's a coil. Okay, that coil symbol is right there. This generates a magnetic field. That magnetic field physically closes a switch. Basically closes the light switch. Okay, or set of contacts, and that's how it energizes this.
Okay.
Okay, and again, we're going to spend some more time on relays and contactors, but just remember that these both are getting full source voltage, so their resistance really doesn't matter.
All right.
Okay? So in a parallel circuit, voltage stays the same at each load. Okay, and amperage adds up. With each load added to the circuit. Power adds up. So if one load is using 100 watts, let's say you have 4 light bulbs in a room, you have one that's using 100 watts, you have another that's using 60, my total wattage is going to be 160. Your total circuit resistance is smaller than the smallest individual resistance. Remember I said we're going to talk about resistance, and it's a little bit weird. Okay, in a parallel circuit, the total resistance of the circuit is smaller than the smallest individual resistance. And you need to remember that statement is probably the most important statement from a troubleshooting standpoint that I can tell you. The total resistance in a circuit is smaller than the smallest individual resistance. That is probably the most important part of troubleshooting that I can tell you. Okay? The current is determined by each load's resistance. The less resistive a load, the higher the amp draw will be. Okay? So the total current draw of an entire parallel circuit system is I1, so the amperage of load 1, the amperage of load 2, the amperage of load 3. The current obviously can be calculated with Ohm's law, or you can measure it. Okay, you're not going to use Ohm's law to calculate current when you're in the field troubleshooting. You're just going to throw a clamp on the thing and measure it. Each load in a parallel circuit uses the total voltage supplied. The voltage drop in a parallel circuit is the line voltage supplied. Okay, in other words, every device is getting the total voltage for the circuit. The resistance is less than the smallest resistance. The total resistance cannot be obtained by adding it all together. Okay, you have to use a resistance formula. Now, this is one that will work, and I'll put this in an easily understandable form. This will work if you only have two resistances. The one I would like you to remember is this one, because it always works. Okay, RT is 1 over the reciprocal of R1 plus R2 plus R3. Sorry, you can't get away from math. Okay, so let me put this in an area where it's easier to understand. And again, I am concentrating on this one here because it works always. It works whether or not you have two resistors or more resistors. Just get used to this one. This is a shortcut, but it doesn't always work. Okay, so if we go over to here, if I said the total resistance, okay, is 1 over R1 plus 1 over R2. If I could type, it would be great. 1 over R3, and so on. So what you do on your calculator, or the phone on your calculator, you have the resistance of load 1. You divide that into, okay, 1. So you're coming up with a decimal. Okay? So if I have three resistances added together, okay, let's say I have a 50 ohm resistor. I'm going to take 1 and divide it by 50. And I'm going to come up with a decimal of 0.02. Okay? Then let's say I have a 100 ohm resistance. Okay, so I'm going to take 1 divided by 100. Okay, it comes to 0.01. Let's just, for the fun of it, toss a third one in here. We'll do a 25 ohm resistance. This first one was a 50. Okay, so I'm going to take 1 divided by 25. Come to 0.04. I'm going to add these together. Okay, so I'm going to come up with my 0.07. Now to find resistance, okay, because right now the formula says 1 divided by RT equals 0.07. Remember, what I do on one side of the formula, I have to do on the other. So RT equals 1 divided by 0.07, or go to my trusty calculator, and I'll take 1 divided by 0.07, okay, and it's 14 let's say 14.3 ohms. Okay, and again, this comes back to my formula that said, my rule that said, okay, the resistance, total resistance, is less than the lowest resistance. Okay, my lowest resistance was 25. Less than the lowest resistance. Questions? Remember, use this formula. If you memorize one formula, it will work every single time. Okay, so back to the final PowerPoint slide, because I cannot only beat this up so long. Okay, power, which is wattage, is the sum of all wattage. So the total wattage is just like amperage. It's the sum of the watts for each individual device. So I have a 60-watt bulb, a 100-watt bulb, another 100-watt bulb. My total power is going to be the 260. We're going to add it all up together. I said a 60 and a 100 and a 100. We're going to add it all together. Power adds, okay? So again, we can add that to our thing. Power adds. Okay. Okay. This is what I need you to know and what I need you to understand. So if anybody is taking screen captures, this is basically what we went over today. It is the most important points of the theory of electrical that we're going to cover, okay, is what I currently have on the screen. So I'm going to leave it there for a minute. As I'm going to wrap this up, I'm going to shut off the recording, and then I'll take any questions anyone has.